All right, so we're going to wrap up probability with sort of AP problems that have multiple parts that kind of shift from one focus to another. And this is one of my favorite problems. Certainly there are many, many other ones that we could use, but this is going to be the one that I've chosen because it's got so much in it probability-wise. So this is all I'm going to show you today. I know that our videos have been a little long, so I'm going to try to keep this one short. So here we go. A candy manufacturer is marketing a gift box containing 4 cream-filled nuggets and 5 pieces of fudge. Right? So kind of keep these separate. The manufacturing process for each candy is designed so that the mean weights of the cream-filled nuggets, go back to blue, cream-filled nuggets is 3 ounces, that's the mean, with a standard deviation of 0.2 ounces. And the mean weight of pieces of fudge is 4 ounces with a standard deviation of 0.3 ounces. The boxes, that's the third component that we've got, have a mean weight of 3 ounces and a standard deviation of 0.1 ounce. So color-coded everything here. Assuming that the weights of the boxes, nuggets, and fudge are independent, what is the mean and standard deviation of the weight of a complete box of candy? All right, so this is combining random variables, and there are 3 of them. There's nuggets, there's fudge, and there's boxes. So let's just go ahead and we'll do the mean first. And let's go ahead and get this a little bit more detailed than this. Let's say it'll be the mean of, we'll call your cream-filled nuggets just N for nuggets. And we'll call your pieces of fudge F. And we'll call boxes B. All right, so if we're just looking at a combination of a single box with all of these 3 elements in it, it'll be mu of 4n, because there are 4 nuggets, and 5f for 5 pieces of fudge, and then plus 1 box. And we can just kind of go ahead and use rules for means on this. So this will be 4 times, let's see, the cream-filled nuggets are 3, so 4 times 3 ounces, plus 5 times, what is it, 4 ounces for the fudge, and then plus 1 times your box, which is 3 ounces. So that'll be 12 plus 20 plus 3, that should be what, 35 ounces? All right, now that's going to be the easy one. The troubling one is going to be the standard deviation, because we have a formula for standard deviation based on variance. Remember this? Variance of, let's say, a plus bx was the formula. We could just ignore the a because that's not going to change anything if you do a transformation on this. And we had b squared times the original variance. And that was fine. Here, though, it's going to be a little bit different from the standpoint that each of your cream-filled nuggets counts as its own random variable. And each of your 5 pieces of fudge counts as a random variable too. Because here it says the manufacturing process for each candy, so that's looking at each candy individually, and the mean weights of, let's see, hang on, and the mean weight of a piece, 1, of fudge is 3 ounces, all right? So to do this, here's how we're going to do this. I'm going to start out with variance, all right? So I'm going to convert this standard deviation into variance, And let's go ahead and just kind of label it the same way we had it. So this would be 4n plus 5f plus b. All right. Well, here is one piece of fudge. All right. It's 0.2 squared. All right. And really that's just going to be 1 in front of this. So I'll just put a 1 here. And that's actually squared too, which is just 1. So I'm not going to change that. So it will be consistent with this formula up here. It's just that this multiplier in front, that factor of 1 squared, is kind of superfluous. So that's for one of the 4. And 0.2 squared is for another. And there's a 1 in front of that too. Plus 0.2 squared plus 0.2 squared. Now you don't really have to do this, but I'm just doing this to demonstrate. And then it's 0.3 standard deviation for your fudge, and that'll be squared. There's a 1 here that's also squared, but we're just not putting it. All right, and I think we have 5 of those. So let me just keep putting them here. All right, so 0.3 squared plus 0.3 squared, that's 4. Plus 0.3, and it's getting weird. Hang on, let me fix that. All right, 0.3 squared. So there's 5 of those, plus your box has a standard deviation of 0.1. So that's 1 times 1 squared times 0.1 squared. All right, so what you end up with here is this. You actually end up with 4, because there's 4 of these 0.2s, times 0.2 squared, and then you end up with plus 5 of these 0.3 squareds, and then you just have 1 of those 0.1 squares. And if you do the math on that, that gives you 0.62. Now that is your variance. All right. In order to get the standard deviation of 4n plus 5f plus b, that's going to be the square root of 0.62. I can get that to right. And so that'll end up being, I'm kind of out of room here, 0.7874. All right, that is your standard deviation for the combination of all of these things. So here's your mean, and here's your standard deviation right here. All right. Most people that mess this problem up don't get this right. They put a square on here and a square on here and a square on here, thinking that they're being consistent with this. But again, you've got 4 of these separate pieces of cream-filled nuggets, and each one has a 1 squared in front of it. And so really that 1 squared just kind of goes away. So you have just this times 4. All right. So what happens though if you don't get this standard deviation right? Well, you're going to drag it down in the rest of your problem, and it's going to make all of those wrong. But the good news is the people that grade this kind of thing are going to be cognizant of that, and so they're going to give you the benefit of the doubt. And if you do the math right and the setups right from here on in with the wrong numbers, you still should get credit. All right. So assuming that the weights of boxes, nuggets, and the fudge are approximately normally distributed, what is the probability that a randomly selected box made up of all of those components of candy will weigh less than 34 ounces? All right, so we're told that this is that X is approximately normal, and we have a mean here of 35. Let's see, 35. And a standard deviation of 0.7874. All right, and if we're going to go ahead and do what we normally do and just create a normal curve representation of the situation, here's 35 and here's 34, and we're interested in everything less. All right, so that's it. We're all set up. So this is the probability that X, any one box, is less than 34 ounces. And that's the same as the probability that Z is less than 34 minus 35, adjusted by 0.7874. And that should get us going because everything is set. All we need now is the normal CDF part. So normal CDF. All right, and so it's going from, remember, negative infinity here. So I'll just put negative 100, something real small, and up to 34. Mean is 35. And standard deviation is 0.7874. And that should give you 0.1020. Nice, all right? So we borrowed this number and this number from the previous problem and just did a standard normal calculation on it. All right, so now to part C. If 3 boxes are selected at random, what is the probability that at least one of the boxes will weigh less than 34 ounces? All right, well, it either will or it won't, right? And wow, that sounds binomial, okay? So X is binomial with n equals 3 and probability of success, which came from here, of 0.1020. So you can see the linkage here, that if you kind of mess up along the way, that it kind of travels down the problem with you. And so at least one, we could do 1 minus the probability of none if you want, but I'm just going to do a binomial CDF. So binom CDF. All right, we want to go, n is 3, right? Probability of success is 0.1020. When you do it on the calculator, the boxes kind of guide you into what order things are. And the lowest value that we're looking at is 1, and then we're going up to 3, and we should get a quick answer for this, 0.2758. All right, so 3 down, 2 to go. We've had a random variable question. We've had a standard normal calculation, a binomial question. Let's see what else they're going to pull out of their hat. So what is the probability that the third box selected is the first box that weighs less than 34 ounces? All right. All right, so here your random variable X is geometric. Right? Because it's the first success by the third box. All right, and it's exactly by the third box, so that's a geomet PDF. And all you need is the probability of success, 0.1020, and the trial that you're interested for your first success, and that'll be the third one. And so that'll be 0.0823. Neat. All right, one more to go. Determine the probability that a random sample of 3 boxes will have a mean weight of less than 34 ounces. All right, so this will be a mean for n equals 3. So that's got to be an x bar, right? So we're looking at the probability that x bar is less than 34 ounces. Well, if the population was normal back here in part B, then we can say that this is normal too, right? This sampling distribution. So x bar is approximately normal. We use the same mean, which is 35. And now the standard deviation is just our old standard deviation, 0.7874, adjusted by the square root of the sample size. All right, so let's go ahead and continue on with what I wrote here. So this is the probability that, let's go ahead and clean that off. This is the probability that x bar, z is less than 34 minus 35 adjusted by square root of 3. And we should be able to just pop this into normal CDF. So normal CDF. All right, and that would be, this is less than, so it goes to negative infinity. So again, negative 100 up to 34 with a mean of 35 and a standard deviation of 0.7874 over the square root of 3. And if you've been watching my videos, you know that that can go in your calculator exactly how I wrote it. All right? And so you're going to get 0.01391. And there you go. So those are all three of, I'm sorry, actually it's 5 different things in the same problem. And that's what AP has to kind of do in order to make a 2-question AP exam actually function to cover the whole course. Now my thinking is that they would probably mix up some probability with some other things that were not probability related, but at least you get some kind of idea of what's going on here. So I put together some multi-step problems, and you can certainly download those. You can download this as usual to work it beforehand or work it alongside with me. And, you know, this will be the next thing on our list of things to do. All right, so good luck with that. And on that note, I am going to sign out and let you go back to your day.